Hello everyone, welcome back to the channel. Today we are entering the world of synchronous motor drives, the technology powering modern EVs, robotics, industrial machines, and even future aircraft. So let us start the journey. If BLDC motors are the heroes of e-bikes and scooters, then PMSMs are the superheroes of electric cars. From Tesla to Tata Nexon EV to BMW i4, PMSMs dominate the EV world because the most important reasons is because they offer crazy high torque, excellent efficiency, smooth acceleration, and silent operation. This is why PMSM drives are everywhere. Now let us understand the PMSM construction. Let us open the motor and see what's inside. Stator, just like any AC machine, three-phase windings. Rotors, here is the magic permanent magnets. These magnets aren't ordinary. We are taking magnets that are stronger than your fridge magnet by a factor of 20 to 30. They can be embedded inside the rotor or mounted on the surface. This construction gives PMSNs a massive torque punch, right? Now understand the PSM working principle. Okay. Now let us imagine you are a merry-go-round. You are on a merry-go-round. The stator produces a rotating magnetic field like a spinning carousel. The permanent magnet rotor tries to lock with its spinning field. Once it locks, it rotates at the same speed. This is called synchronous motor. No slip, no delay. Just perfectly synchronized relation. Alright. Now let us see what is a regenerative braking in this. When the vehicle wants to slow down, PMSM performs a magic trick. It switches roles from motor to generator. The spinning rotor induces voltage, current flows back to the battery, and you get energy recovery, battery recharging, extended driving range. This is why EVs feel smooth when slowing down. They are saving energy instead of wasting it as heat. Now let us talk about now let us talk about PMSM speed and torque characteristics. In this, there is a constant torque region. It is shown in the graph. This shows that up to the base speed, the motor gives flat and delicious torque, which is perfect for acceleration. The next is we can see there is a field weakening region. Above base speed, torque slowly reduces but power stays constant. This is how EVs reach high speeds without gears. Now let us discuss what is high torque density. In this we can see small motor is having huge performance. So EV manufacturers is usually love this. So now let us see what is closed loop control with PI controller. Imagine driving an EV, you press the accelerator. You expect the car to respond instantly. The PI controller makes sure that happens. The P term reacts quickly to speed error like a fast correction. The I term removes leftover errors slowly. Together they ensure no jerks, stable acceleration, perfect speed tracking. Alright. So without a PI controller, your EV would feel sluggish or unstable. So the PI controller continuously compares the reference speed or torque with the actual feedback, generating a corrective signal. The proportional term responds to the instantaneous error. The integral term eliminates steady state error, together ensuring precise, stable motor control. Now the next slide is related to the PMSM vector control, that is field oriented control. Thinking of it like splitting the motor current into a flux part and the torque part. Just like how we control DC motors independently, right? So vector control ensures you have high efficiency, faster acceleration, instant torque response, and smooth operation. This is why EVs feel buttery smooth when driving. Now come back to the synchronous reluctance motor. In this motor, let us meet the synchronous reluctance motor. Here we have no magnet. Like we can say, a magnet is free alternative gaining traction in EV and industrial applications, right? So there are no magnets, no rare earth materials, and no expensive rotor. Yet it still achieves synchronous operation. How? How? This can happen only by magnetic reluctance. Just like water flows through the easiest path, magnetic flux also prefers a low reluctance path. The rotor constantly adjusts itself to flow to follow the magnetic field, creating torque. So in this way, we can understand that synchronous motors exploit magnetic reluctance to produce torque, offering a compelling balance of cost, efficiency, and robustness. Now let us look towards synchronous rotor construction. The figure shows that there is a stator, rotor, and flux barriers. Now how does it works? Yes, you see the flux barriers. It is like the slots which cut in the special pattern. These barriers create. So here the slots actually create low reluctance in the D axis and high reluctance in the Q axis. If you see towards the rotor looks very different here. So this reluctance difference produces reluctance torque. The design looks weird, but it works beautifully. Now you understand this salient rotor design has flux barriers which create high reluctance in Q axis and low reluctance in the D axis, producing reluctance torque. In this operation, the rotor locks to the rotating stator field running at synchronous speed with no slip. Alright. Then now we will see its working principle. The rotor wants to align with the stator field, just like a compass aligns with Earth's magnetic field. Because it always tries to reduce reluctance, we get rotation, and because there are no magnets, synchronous motors are cheaper, more robust, and suitable for high-speed operation. So many EV companies are now exploring synchronous motors to cut costs. Now let us see what are the applications in electric vehicles. So where do synchronous motors shine? First of all, they are affordable electric scooters. They are budget passengers EVs, hybrid electric vehicle, auxiliary drives, industrial applications. So there are many applications. Here also we can see they are cost effective, robust design. There it has a high efficiency, especially with advanced vector control, and the design is mechanically very strong at high speeds. And of course, cost effective. So as there are no rare earth magnets, so lower material cost and supply chain risk. So what are the advantages of it? As there are no magnets, no dependencies on China's rare earth market, they have high mechanical strength, good efficiency with advanced control. So what are the challenges here? Since slightly higher torque ripple and lower power density than PSM. So it has a higher torque and the power densities than PMSM. So now let us compare first of all the PMSM versus synchronous motor. They are two like a boxing match, right? PMSM has a high torque, compact, super smooth, and expensive. But if you see to the synchronous motor, they are very cheap, robust. There are no magnets, slightly lower torque. So if you want high performance, PMSM wins. And if you want cost effectiveness, synchronous motor wins. So both motors depend heavily on control strategies. Without vector control and PI control, neither PMSM nor synchronous motor can deliver high performance. So modern electrical vehicles survive on real-time control, high-speed sensors, and advanced algorithms. So the motors are strong, but the controller is the real genius. So to wrap up, the PMSM is a superstar of electrical vehicles which has high efficiency, high torque, and high performance. Synchronous motor is the rising star which has affordable, durable and improving every year. And modern control, that is PI and field oriented control, makes both motors shine. So understanding these motors is essential for anyone entering the EV industry. Thank you so much for watching. If you learned something new, hit the like button, subscribe, and share it with your friends. See you in the next lecture.